Okay, we've talked about light. What is light? We know it can be talked about as a bunch of particles, we call them photons, or as a wave, or we call it electromagnetic radiation, electromagnetic wave, still light. There's non-visible light that our eyes aren't tuned to, and there's light that our eyes are tuned to. We know that the energy of light, the ability to do something, is related to the amplitude. So low amplitude means less energy, high amplitude, more energy, and the frequency. Low frequency, less energy, high frequency, higher energy. Good. So that idea we need to keep. Then we talked about the spectrum of light. So let's look at how this ties in. Remember, why we need to know this is because we can't go anywhere except our solar system, our hood. Right? We can send probes, but they can take a long time to get there, right? So beyond our lifetime. So all we can do is look. So let's see what's coming in from space. We know that light travels very fast, the speed of light. It travels 93 million miles. What's that? 1 AU, 1 astronomical unit, in about 8 minutes, a little over 8 minutes. Right? So for light to be traveling 8 minutes and travel 93 million miles, if it's traveling, light is traveling for a year, that's a long ways. 6 trillion miles? Hard to imagine. And even then, the light from the closest star wouldn't have gotten to us. The light from the closest star has got to travel 4 years, 4.2 years. Crazy. I can't even imagine that distance, and I teach it. So what am I going to do? But there's stuff out there. There's stuff out there. Our planets are close to us. We can go to them. There's stuff way out there. Within our galaxy, there's stuff close to us. There's stuff way out in our galaxy. And there's other galaxies. So let's try to break it down. So what happens? Well, let's see. We know that our spectrum of light, our range of light, goes from low frequency, meaning low energy, and then the energy becomes more and more as the frequency becomes higher and higher. Higher energy, different frequencies of infrared. There's a whole range until you start being able to see it with your eye. Good old Roy G. Biv, the colors of a rainbow. And there's different frequencies of red and different frequencies of orange and different frequencies of yellow, and it gradually goes from different frequencies of green, blue, violet, and then your eye can't see it anymore. Right? Your eye isn't designed to see the ultraviolet, but that's higher frequency, so higher energy, X-ray, higher frequency, higher energy, gamma ray, higher frequency, higher. So there's a range, and we give them these names, right? But clearly this is visible light. What happens? Well, first off, where do they come from? So it's coming into Earth's atmosphere and hitting our ground, or is it? I mean, we want to see what's out there from Earth. So what do we have? We have space stuff. Exploding stars, galaxies, clusters of stars, whatever's out there, we want to be able to see it. We can't see it with our eye because it's too far away, it's too dim. So we need telescopes to gather it. Okay, well, we want to look at it basically. Well, if this is low frequency, low energy, then you're going to have cool stuff creating these. And there's some other factors too. But so there's stuff here that's not going to be as hot. And you got stuff like sun creating this range in here. So hotter. Whatever you can see. Stars. Creating that. And that can create a range of things, right? And just get this idea that in order to create this, it's got to be really hot. So exactly like an exploding star. You know, things that have a lot of energy are going to create this stuff. So hot stuff. Exploding stars is a good example, right? Something crazy. All right, so we want to see all that stuff, right? We want to see it, and we might not see it here. So we've got to take that image, and then what we do is take that light and convert it so our eyes can see it. Or we just use the data when you're actually doing the analysis. You don't care about a picture. You look at the data and see what you've got. So what happens is this light comes through. Well, as the light comes through, interesting thing happens. You kind of know this. This is chapter 5, right? I mean, for example, infrared. Infrared comes in, and you can't see it, so I like to do the dotted thing. You can't see that. I can't see it. It comes in pretty far. Right? And we got good old greenhouse gases in the troposphere. Carbon dioxide, water, methane, and no go. It blocks a lot of the infrared. A little bit gets through it. Blocks that pretty well. All right, so we know that from chapter 5. And we know from chapter 5 that, of course, and we just know from stepping outside that red gets through, and orange and yellow get through, right? And green gets through. It might bounce around a little bit, but kind of gets through, right? We know that. And we know blue gets through. We know that along the way, though, our atmosphere is such that the blue starts spreading all out, making a blue sky, right? Okay, that's why we have blue sky, and blue gets through. And the violet gets through. So that's fine. We could have telescopes to see out there, right? But what if we put a telescope here to see infrared? That's a problem. We can't see that. What about ultraviolet? Uh-oh. Good old ozone blocks it in the stratosphere, right? What's that? That's 3 oxygens tied together, whatever. Okay, so we can't see the stuff that's creating UV, or the UV created by the stuff, by the sun. And what about X-rays? Do you want high energy? You don't want this sterilizing UV to hit the planet. You don't really want to go outside and sunbathe in the X-rays. So happily, this high energy stuff gets blocked. Good for Earth, good for life. Not good for astronomy. There's information there that we're missing out on. We can't put these telescopes here on the ground. Doesn't make any sense. They're not coming through. All right, cool. Now they do get absorbed in different layers, and you could look at that readily on the internet. I don't think you need to obsess too much. If you get this point, that's good. Well, let's go over here. What about microwaves? Now remember, microwaves, we say it's low energy, but if you have a lot, high amplitude, which is a lot of microwaves, you can cook your food. Right? So, but good news, not so much, right? Not coming through. Radio, well, not all the radio comes through, but a lot of it does. I mean, the cool thing about radio is it goes right on through stuff. We've got a little radio here. It's not an MP3 player. It picks up radio waves. It comes through the walls, and we've done this before. Right? It's coming through. That's radio waves at the speed of light, right? And it goes through walls. It goes through stuff. Okay, so cool. That goes through, and radio astronomy has been very, very valuable in the last 20 years. It's just incredible. Why? Because even though dust might block stuff, it can block light and stuff, the radio waves can get through, and we can see deeply through stuff into space and so on. So radio waves are great. So let me see, how do I put telescopes on the ground? I want to see that stuff. All right, well, I can put radio telescopes, and those are the big guys, right? Those are the big ones that you'll have here on the ground. Nice big dish, kind of tied up like that. You'll see it. And these things are big, right? Little thing looks like that. This is a radio telescope. You can put that on the ground because you can receive stuff. Now, you're not going to get radio stations from space. You're just going to get signals from cool stuff and whatever information you can get. All this stuff is coming towards Earth. Earth is bathed in this, but we can't, there's no sense. Microwave, infrared, it's not very good, right? Oh, we can put optical telescopes. So an optical telescope are for visible light. Right? So you can go ahead and look up, get your backyard telescope, whatever you got there, a little finder scope in there and things like that. And you can see it out there. So that's cool. That's good. Stargazing, look at Jupiter and so on. If that didn't come through, you couldn't even see Jupiter. We wouldn't see any stars. We wouldn't see the sun. We wouldn't see the moon. That stuff comes through. That's what we see. Does this come through? Not so much. A little bit comes through, but not too much, right? So ultraviolet telescope here, and little different design here. So not so good. No good there. We're missing a lot of information. So let's talk about these problems on the next one. We'll talk a little bit about telescope design. Okay, let's take a look. So you know what the goal is. We want to look into space. We want to see where we came from, what's out there, etc. the atmosphere has issues. The issues with the atmosphere is air moves around. You've got water in the air. You've got air pockets that are warmer and cooler, and things move around. And as the starlight comes through it and that air is moving and you've got stuff going on, the stars twinkle. Without that, the stars don't twinkle. With a really good telescope out in space, you're going to see just dots of light. They're so far away. So that's why stars twinkle, because they're coming through the atmosphere. The other big problem is that not all the frequencies come through, as we just said. That is huge. Right. Now, of course, you can have clouds. Well, obviously that's bad for visible. We just had the lunar eclipse. I'm waiting, and it clouded over. I couldn't see the visible light with my eyes, right? But a radio telescope, just like the radio comes through the wall, that's okay. Radio can see through the clouds. It comes through, right? Cool. Pollution, particulate matter, yuck stuff, methane kind of stuff, and things like that. It's hard to see through, clearly. Makes pretty sunsets, but pollution. Now there's another kind of pollution. So this is particulate matter from cars and factories and so on, but light pollution. So you can go on the web, look at Palomar in the 1950s, and now look at Palomar now, down there kind of LA, San Diego, in that area. Look at the sky. You'll see pictures. Look at it on the internet. It's crazy. Right now you've got casinos there, the light goes up, it reflects off of the atmosphere, and the whole atmosphere is aglow. If you live near a city, you see that. If you have a neighbor that's not so aware, they might have a light that's going all directions. That's kind of wasted. You don't need to, illuminate the birds, right? So if you cap it, you can use a lower wattage bulb and save energy, reduce pollution, and reduce light pollution. So city planners need to be aware of this. You need to cap, and you can make them lower, spread them out, and not illuminate the sky. Because what happens, the sky gets so bright that it's brighter than the stars or many of the dimmer stars, right? The higher apparent magnitude, higher M number, right? So the sky is brighter than the stars, and you're not going to see the stars. In the daytime, there's stars out there, there's planets out there, and you can't see them because the sky is too bright. But that's no one's fault. It's the sun's fault, right? So what's the solution? So the solution here, real quick, is it kind of makes sense. You can either put telescopes on high, dry, clear mountaintops, so you look for these places, maybe in Hawaii or Chile, wherever you got it, Puerto Rico, mountaintops. And so, for example, see the Keck twin telescopes. And they're like 10 meters, think 10 yards in diameter. These things are great. They're huge, and they're made of individual mirrors that you can readjust and focus nicely. And they're up there on the mountaintop. So if you got a mountaintop, you might be able to come up here and grab some of that infrared, and maybe grab some of that UV. And so you'll see optical telescopes. It's nice. You don't have to worry about all that stuff. You can see a little bit infrared and UV telescopes. Radio, pretty big. Maybe you just want it down here, but you can put them up there too, right, of course. But maybe you say that's not enough. I'm still missing stuff, so what do you do rather than mountaintops? Well, you go into space. So good old space telescopes. A space telescope, ST. You put it in, now where do you do it? Well, ST, space telescope, where usually it's in orbit. You don't have to go very high to go into orbit, right? 300 miles, you're past it all. You're out there, looking out there. There's no blue sky when you head out there. You got none of these problems. So space telescopes are great, and the two that you should be aware of is the Hubble Space Telescope. Hubble, great astronomer, space telescope. And you got the JW, James Webb Space Telescope. And you might check those out. They were, much of that was created here in Richmond, California, San Pablo, California area. at Hilltop, at the Tinsley Labs, great stuff, neat connections. This one, 1990 to 2010, good 20-year span of incredible success looking out in the optical range and seeing fantastic photos that we all just love and their artistic compositions. James Webb Space Telescope is going up. We'll see how the economy goes and things like that, but around, who knows, 2019-ish, and it'll go up. It's not going to look in the visible, so not so much pretty pictures, but it will look deep into space and see this stuff, and hopefully look so far away that the light will have traveled from since the beginning of our universe in that region. So it's exciting. So let's look at telescope designs here next, just basic things, and hopefully this helps augment the text. Okay, see ya.